Tonight, we're going to do something very quiet universe. We're going to look at surprises, real surprises, without turning them into panic. We're going to let the data feel a little strange, let our expectations wobble a little, and then watch how science steadies itself again. Because in astronomy, anomaly doesn't mean the universe is broken. It usually means we asked a question and the universe answered more creatively than we expected. Our topic is the early universe, the era sometimes called cosmic dawn, and a set of puzzling findings that have been widely discussed since the James Webb Space Telescope began producing deep images and spectra. The headlines at times have sounded dramatic. Galaxies too big too soon, black holes too massive too soon, objects that look like something we don't quite have a box for yet. But if you slow the story down, the tone changes. The early universe is difficult to observe. The light is faint, stretched and filtered through dust. And the models we use are not fragile castles, they are adaptable frameworks. When new observations arrive, models don't collapse. They bend, they refine, they update their assumptions. That is how progress looks when you watch it in real time. If you're listening late at night, you don't need to hold on to every detail. Just let the main thread stay with you. Webb made it easier to see very distant, very young galaxies. When astronomers looked, they found more bright candidates than expected, and some of them seemed surprisingly massive or surprisingly mature. Then, as spectroscopy improved and interpretation matured, some tensions softened, while other puzzles deepened, especially around a mysterious population nicknamed the Little Red Dots. This episode will move like a calm walk. First, we'll set the stage, what early universe means in time, what redshift means in a gentle way, and why Webb's infrared vision changes the landscape. Then we'll talk about the oversized ancient galaxies conversation, why early photometric estimates sometimes made galaxies look heavier than they were, and why that didn't make the data wrong, it made the uncertainty visible. NASA has even published updates emphasizing that some early mass estimates were revised downward once key effects were accounted for. After that, we'll linger on the little red dots, small, very red objects that appear abundant in Webb surveys, often around the first billion years of cosmic time, and that may involve faint active galactic nuclei or something even more exotic. And finally, we'll talk about what it means for models to rethink, not as a dramatic rewrite of everything, but as a careful rebalancing. What changes when we include more dust? What changes when we separate starlight from black hole light? What changes when we realize that in the young universe, a small object can shine in a way that tricks our intuition? Before we begin, a small invitation. If you have a habit of watching cosmic news like it's a scoreboard, Webb beats the model, Webb breaks cosmology, try setting that aside for tonight. The early universe is not a debate stage, it's a landscape, and Webb is giving us a new flashlight. Now, let's define cosmic dawn in a quiet way. The universe is about 13.8 billion years old. When we speak about the early universe, we often mean the first 1 or 2 billion years, when galaxies were assembling quickly, stars were forming at high rates, and the first massive structures were taking shape. Light from that era has traveled a long time to reach us, and as the universe expanded during that travel, the light stretched, its wavelength became longer. That stretching is what we call redshift. Redshift is not only a number, it is a translation. It tells us how old the universe was when the light left its source. Higher redshift means earlier time. It also tells us that the light that began as ultraviolet or visible may arrive to us as infrared. That is why infrared telescopes are so powerful for cosmic dawn. They are tuned to where the early universe's light has moved. Webb was designed for this. Its mirrors and instruments are optimized to detect faint infrared signals, to see through dust, and to take spectra, rainbow-like decompositions of light that reveal chemical fingerprints and distances. When Webb's deep fields arrived, astronomers saw something that made them pause. A large number of bright galaxy candidates at very high redshift, and some of them seemed too massive, too structured, too mature, too soon. But more than expected immediately raises a question. Expected by whom and under what assumptions? That question, slowly and kindly, is where the anomalies begin to become understandable. In the next file, we'll talk about what the early claims were actually based on, why early mass estimates can be fragile, and how the story matured as the data grew deeper and more precise. In the first wave of Webb results, some of the most talked about numbers were not directly measured, they were inferred. That's important to say out loud because it changes how you hear the rest of the story. In astronomy, we often work in inference first, then confirmation. We see a color, a shape, a brightness, and we estimate a distance. Then we collect spectra and refine. Early Webb deep fields were stunning in sensitivity, but many early claims relied on photometry, measurements of brightness through different filters, rather than on detailed spectroscopy. Photometric estimates can be powerful. If an object is very faint in visible light and bright in infrared, that pattern can suggest high redshift because the object's ultraviolet light has been shifted into infrared. But photometric estimates can also be fooled. Dust can redden light. Strong emission lines can make a galaxy appear brighter in certain filters, making it look like it has more starlight than it actually has. And lensing, gravity-bending light, can amplify brightness. So when early candidates were described as massive galaxies at extreme redshift, a quiet caveat was always there. These were best fit models under uncertainty. They were not final weights placed on a cosmic scale. This is why the conversation became so intense, because mass in astronomy depends on modeling the stellar population. You don't count stars one by one, you infer the total mass from the galaxy's light, and that inference depends on assumptions about the ages of stars, the history of star formation, the distribution of stellar masses at birth, and the amount of dust. If a galaxy's light includes a significant contribution from an accreting black hole, an active galactic nucleus, then you can overestimate how many stars are required to produce the observed brightness. Likewise, if a galaxy has strong emission lines, those lines can artificially boost the brightness in certain filters, making the galaxy look like it has more starlight than it actually has. So, the first lesson of the early Webb anomaly era is not the model is wrong, it is the mapping from light to mass is delicate, especially at high redshift. But delicacy does not eliminate genuine puzzles. Even after revisions, Webb has shown that the early universe contained a rich variety of luminous systems. Some appear very dusty, some appear compact, some appear to host rapidly growing black holes. A discovery can be partly an artifact of early inference and still remain partly real. This is where the most interesting scientific work happens, in the narrowing. Astronomers began to ask more precise questions. Instead of, are early galaxies too massive, the question becomes, how common are the brightest galaxies at a given redshift, and what fraction of their light comes from stars versus accretion, and what physical conditions could produce these spectral signatures. Spectra help because they can show you specific emission lines, like hydrogen, oxygen, or other elements. These lines can confirm redshift more robustly than photometry. They can also reveal whether a galaxy is dominated by star formation or includes an active nucleus, because broad lines and certain line shapes can indicate fast-moving gas near a black hole. As this careful work expanded, it set the stage for a new kind of anomaly, one that is less about sheer mass and more about classification. Not galaxies that are simply too big, but objects that don't fit cleanly into the usual categories of star-forming galaxy, quasar, or dust-obscured system. That is where the little red dots enter the story.
If you want to keep a question in the back of your mind, here is a gentle one. When you hear that an early galaxy seemed too massive, do you instinctively blame the measurement, or do you instinctively suspect new physics? There is no right answer. It's a personality difference. If you want, comment one word: measurement or physics. The answer helps me know how you like these episodes paced. In the next file, we'll meet the little red dots, what they look like in Webb images, why they're called that, and what they might be, based on the best current evidence and on the open debates. The phrase "little red dots" sounds almost playful, but in practice it has become a serious label for a serious puzzle. Astronomers noticed an unexpected population of compact, very red sources in deep Webb images. They appear small on the sky, sometimes nearly point-like, and they have colors that suggest either heavy dust, older stars, or unusual emission. The nickname stuck because it describes exactly what you see: a field full of galaxies, and among them, tiny red points that don't behave like ordinary galaxies in the same data. What makes them puzzling is not only their color, it's their combination of traits. They can be numerous in certain redshift ranges, especially around the era when the universe was less than 1 billion years old. They are compact, suggesting small physical sizes. Some show evidence for broad emission lines in spectra, which can indicate fast-moving gas near a massive black hole, like a faint active galactic nucleus. Other diagnostics complicate that picture, suggesting that not all of them behave like classic AGN. This is a classic scientific situation. The data are rich, but the interpretation space is wide. So, what are the main interpretations? Let's lay them out in a calm way, as a menu of possibilities. One possibility: they are dust-obscured AGN. A black hole is accreting matter, producing a compact source of light that is then reddened by surrounding dust. The broad emission lines and compact appearance can fit this. In this view, LRDs could be the early universe's hidden black hole growth phase, faint in some bands, but detectable in infrared with Webb. A second possibility: they are extremely compact star-forming galaxies with unusual conditions. If star formation is intense and dust is present, the light can redden. Strong emission lines from ionized gas can distort broadband colors. In this scenario, the LRDs are galaxies, but they are galaxies with extreme star formation and dust, not just normal galaxies at high redshift. A third possibility, they represent something transitional or mixed, galaxies where both rapid star formation and accreting black holes contribute. This is not exotic, it is common in the local universe in various forms. But in the early universe, the balance may be different, and the timescales may be shorter. A small object might cycle quickly between starburst-dominated and AGN-dominated phases, especially if gas inflows are episodic. And then there are more speculative ideas that sometimes appear in public discussion. Some proposals suggest LRDs might be black hole stars or other unfamiliar objects. These remain speculative, but they illustrate how the LRD puzzle invites creative theorizing. In science, the rule is gentle. Ideas are welcome, but they must earn their place through predictions and tests. Why does any of this matter? Because LRDs sit at the intersection of two growth problems: how galaxies assembled their stars and how black holes assembled their mass. If LRDs are faint AGN, then we are seeing a widespread population of early black holes that may contribute to reionization or to the early energy budget. If they are compact starbursts, then we are seeing star formation operate in an extreme dense mode. If they are mixed, then we are seeing co-evolution at a speed and intensity that is unfamiliar by local standards. This is also where "models must rethink" becomes an understandable phrase. The models are not only cosmology, they are the subgrid recipes in simulations: how gas cools, how feedback works, how dust forms, how radiation escapes. Webb is showing us regimes where these recipes may need refinement. If you want a gentle interaction prompt here, which explanation feels more intuitive to you for a mysterious red point in the early universe? Dusty star formation or a hidden black hole? Comment one phrase: dusty stars or hidden black hole. Your intuition doesn't need to be correct. It just tells me which direction to lean in future episodes. In the next file, we'll zoom out from LRDs and ask, what exactly do we mean when we say the model must rethink? Which parts of the modeling stack are most sensitive to these anomalies, and which parts are already absorbing the new information calmly? Let's slow down and look at why this particular nickname took off so quickly. In deep surveys, astronomers usually find populations that vary smoothly: brighter or fainter, bluer or redder, larger or smaller. The little red dots felt different because they looked like a new cluster in parameter space. Many were compact in a way that placed them near the point spread function of the telescope, and many were red in a way that didn't line up cleanly with typical star-forming templates. That combination, tiny and red, immediately invites a short list of causes. If the light comes from a compact accretion engine, you expect the morphology to be concentrated. If dust wraps that engine, you expect the spectrum to redden. If the source is a compact starburst, you still expect concentration, and you can still get redness through dust. But if the source is a more extended galaxy with older stars, you would usually expect a less point-like appearance. So the shape itself is a clue even before the spectrum arrives. Another reason LRDs matter is how they complicate the phrase ancient galaxies. Many of these sources were initially discussed in the same breath as mature galaxies because their colors can mimic evolved stellar populations. But the early universe does not have the time budget for truly ancient stars in the everyday sense.
If an object at very high redshift looks as though it contains a large population of old stars, that can be a modeling artifact. Dust and line emission can create false age. This is why observers and modelers have been cautious. The best current approach is to treat redness as an observation, not a conclusion. Redness is a fact about the light. The cause of the redness is the puzzle. If you're curious about how the puzzle is tested, here are a few calm diagnostics that are often discussed. Line widths. If permitted emission lines are very broad, that often signals gas moving at high velocity in the gravitational field of a black hole. Line ratios. Certain combinations of lines can indicate whether hot young stars or an AGN is dominating the ionization. Mid-infrared behavior. Dust heated by an AGN can show different colors than dust heated by stars. X-ray and radio follow-up. If a source is an AGN, it may produce high energy or radio emission, though heavy obscuring can hide it. Variability. Compact engines can change over time, leaving a subtle fingerprint in repeated observations. None of these tests is perfect alone, but together they can narrow the range of plausible explanations. In a quiet way, this is the beauty of astronomy. You don't need to touch the object. You listen to its light from different angles and at different wavelengths, and you build a consistent story. If you're still awake, consider this gentle question. If you could ask one question of a little red dot, what would it be? What are you made of? How fast are you growing? What will you become? If you want, leave your question as a comment. I read them, and they shape what we explore next. Now we can move outward, from the mystery objects themselves to the broader process of model revision.
When people say that Webb's discoveries challenge the models, it can sound like a single monolithic model is being attacked. In reality, there is a stack. At the bottom, there's cosmology, the overall framework for the universe's expansion, its composition, and the growth of large-scale structure. Above that, there is structure formation, how dark matter halos assemble and merge. Above that, there is baryonic physics, how ordinary matter, gas, dust, and stars moves, cools, forms stars, and responds to feedback. And above that, there's the observation pipeline, how we convert photons into catalogs, and catalogs into physical parameters like mass and star formation rate. An anomaly can live in any layer of the stack. If you find too many bright early galaxies, is the problem the cosmological framework? Or is it that your assumptions about dust attenuation, star formation efficiency, or emission line contamination were too simple? Or is it that lensing magnified more galaxies than expected in your field? Or is it that photometric redshifts were misassigned because certain templates were incomplete? The calm approach is to explore the most flexible layers first. Observational systematics and astrophysical modeling can often absorb new findings without requiring a rewrite of cosmology. That does not mean cosmology is immune to challenge. It means it is not the first lever to pull. This is why over the last couple of years, many early crisis narratives softened. Some early mass estimates were revised downward. Some early bright candidates were confirmed as high redshift, but not as extreme in mass as first claimed. Other candidates were reclassified once spectra arrived, and the community began to build more consistent comparisons between Webb observations and simulations, accounting for selection effects. But even when the mass crisis softened, Webb continued to reveal genuinely extreme objects, especially dusty, compact systems and early black hole growth. In some cases, the language used in popular coverage emphasizes how hidden black holes might dominate the light in certain compact red objects, implying black hole growth may outpace host galaxy growth in some phases. So, what do models rethink? One area is star formation efficiency. In some early halos, gas may have turned into stars faster than typical prescriptions assumed. Another is dust. Dust formation and survival in the early universe can be rapid in certain environments. Dust can both hide star formation and alter observed colors. Another area is feedback. The energy and momentum injected by stars and black holes can heat or expel gas, changing how fast a galaxy grows. The details of feedback are notoriously complex, and Webb's data provide new constraints. Another area is black hole seeding and growth. If faint AGN are abundant at high redshift, then black hole growth may be widespread earlier than previously inferred. That feeds into questions about how the first massive black holes formed. Light seeds from massive stars, heavy seeds from direct collapse, or multiple channels operating in parallel. And another area is the interpretation of light itself. Emission lines can be strong in young galaxies, and when they land inside broadband filters, they can mimic a heavier stellar population. Stellar population synthesis models must be tuned for low metallicity, high ionization, and unusual star formation histories. If your templates are tuned to local galaxies, the early universe will look anomalous. In quiet terms, this is not a Webb versus the Big Bang story. It is a Webb versus our simplified assumptions about the early universe's messy astrophysics story. But it is also true that cosmology is part of the conversation. If, after careful modeling, the number densities of bright early galaxies remain higher than predicted, then you might need to revisit aspects of structure growth, star formation duty cycles, or even the mapping between redshift and distance. The community is actively weighing these possibilities. A quiet mindset helps here. Science is not embarrassed by revision. Revision is the mechanism. If you want one more interaction prompt, when you imagine a model, do you picture a rigid rulebook or a flexible map that improves as we explore? Comment rulebook or map. Next, we'll take a closer look at one of the most common sources of early tension, the conversion from observed brightness to inferred stellar mass. We'll keep it gentle, but we'll show exactly why a tiny red dot can look like a giant ancient galaxy if you don't separate the ingredients of its light. To make this more concrete, it helps to think about the kinds of models astronomers actually use. Some are large cosmological simulations that follow dark matter and gas across huge volumes, forming galaxies within a framework that is broadly consistent with the standard cosmological picture. These simulations must include subgrid physics, recipes for processes that happen below the resolution scale, like star formation in molecular clouds and small-scale feedback. Other models are semi-analytic. They track dark matter halos and apply physically motivated rules for how gas turns into stars, how mergers occur, and how feedback suppresses further growth. The details of feedback are notoriously complex, and Webb's data provide new constraints. And then there are the observation side models, the templates used for photometric redshifts, the stellar population synthesis codes used for SED fitting, and the priors used to decide what a reasonable galaxy at a given redshift should look like. A key point is that these pieces interact.
If your photometric redshift template set is incomplete, you might place an object at the wrong distance. If your SED models underrepresent strong emission lines, you might overestimate mass. If your simulations underestimate burstiness, you might underpredict the number of bright galaxies visible at a moment in time. So, rethinking often begins with a very practical step: expanding the library of allowed behaviors. In the Webb era, that expansion has included a more careful treatment of nebular emission lines, more flexible star formation histories, more realistic dust geometries, and more explicit modeling of mixed star plus AGN light. It has also included a more careful statistical framework. Instead of quoting a single best fit mass or redshift, many analyses now emphasize posterior distributions, ranges of plausible values, weighted by the data and priors. This is where the calm precision of science lives, not in the loudest number, but in the shape of the uncertainty. And if you ever wonder why scientists sometimes disagree in public, this is a quiet reason. Two teams can use the same data and choose different priors or template sets, leading to different best fits. Over time, the community converges by comparing methods, by cross-checking against spectroscopy, and by asking which assumptions are most consistent across multiple surveys. If you want to imagine this process visually, think of a map drawn in pencil. Early lines are faint and uncertain. As more measurements arrive, the lines darken, the coastlines sharpen, and the empty areas fill in. The map is still the same map, but it becomes more truthful. Next, we'll return to the most important translation step in this whole story: how brightness becomes mass, and how a compact red object can pull our models toward the wrong corner of the parameter space if we let it. Let's talk about the quiet alchemy of astronomy, turning light into mass. When you see a distant galaxy, you see a blend of many components. You see starlight from populations of different ages. You see dust absorbing and re-emitting energy. You see emission lines from hot gas around young stars. You might see a light from an active nucleus. You might see lensing magnification. And you see it all through the filter set of a telescope. To estimate a galaxy's stellar mass, astronomers often use something called spectral energy distribution fitting, SED fitting. You compare the observed brightness in different filters to a library of model galaxies with different star formation histories, ages, metallicities, and dust contents. The best fit model gives you an inferred mass. This is a powerful method. It's also a method where assumptions matter. If your model assumes the light is mainly from stars, but in reality a faint AGN contributes significantly, then the model will explain the extra light by adding more stars, raising the inferred mass. If your model underestimates emission line contributions, it can misinterpret bright filter measurements as continuum starlight. If your model assumes dust behaves like it does in nearby galaxies, it may misread the early universe's different dust chemistry and geometry. So when the earliest Webb catalogs produced some extremely massive candidates at very high redshift, part of what we were seeing was the boundary of the modeling library. The early universe was asking, do your templates include the kinds of galaxies I can actually build? Over time, the libraries improved. The community learned to treat certain photometric bands with caution when strong lines could contaminate them. Spectra arrived, anchoring redshifts. Some candidates moved to lower redshift. Others stayed high redshift, but with revised properties. If you find this comforting, it should be. It means the scientific process is working as intended. Early inference, then correction, then deeper understanding. But now, let's return to the little red dots through this lens. Why are they red? A red color can mean several things. It can mean old stars, stars that have cooled and reddened, implying an evolved population. But in the early universe, old is relative. At high redshift, the universe itself is young. A galaxy can have relatively old stars for its era, but the absolute ages are still limited. So if an object looks extremely red, dust becomes a strong suspect. Dust can absorb blue and ultraviolet light and re-emit in infrared. A red color can also come from a sharp spectral break. The Lyman break, caused by absorption of light shortward of a certain wavelength, shifts with redshift and can produce strong color changes between filters. That's one reason high redshift candidates can appear red in certain filter combinations. And then there is the possibility that a compact AGN is producing a hot continuum that is then reddened, or that broad emission lines contribute strongly in specific bands. This is why LRDs are a perfect test case for the light-to-mass problem. They are compact, they are red, and they may blend multiple components in a way that tempts our fitting methods to misassign the ingredients. In a quiet way, you can think of it like listening to a choir behind a curtain. If you only hear the combined sound, you might assume there are 50 singers. But if there's also a strong echo in the room, or a hidden soloist with a microphone, you could be fooled. To estimate the true number of singers, you need to separate the voices. Spectroscopy is like opening small gaps in the curtain and hearing individual parts. This brings us to an important scientific virtue: humility about uncertainty. In the early universe, even Webb sometimes operates near the edge of detection. The faintest objects require careful background subtraction. The reddest objects require careful calibration, and small systematic shifts can change inferred masses significantly. So when you hear anomalies, you can translate it as the early universe is teaching us where our inference pipeline is sensitive. If you want a calm question, do you prefer the story where the universe is surprising or the story where our measuring tools are learning? They're both true, but people lean one way. Comment universe or tools. Next, we'll zoom in on what makes LRDs so visually and physically compact. We'll talk about size measurements, why compactness is itself a clue, and how small objects in the early universe can have an outsized influence on reionization and black hole growth. There is another subtle effect that often appears in early universe discussions: a preference for the brightest outliers. If you search the deepest images for the earliest objects, you will naturally notice the ones that are unusually bright. But the brightest objects can be bright for multiple reasons: intrinsic luminosity, strong emission lines, brief starburst phases, or gravitational lensing magnification. If you don't account for that mixture, your typical early galaxy can start to look more extreme than it really is. This is one reason astronomers pay attention to selection functions and completeness. It's not just philosophy,
It's how you avoid mistaking the top 1% for the whole population. Now, let's add one more layer of calm complexity to SED fitting: degeneracy. A young, dusty galaxy can look similar in broad colors to an older, less dusty galaxy. A galaxy with strong emission lines can look in certain filters like it has more continuum starlight than it does. An AGN component can mimic a hot stellar population. The fitting code has to decide which combination best explains the data. When you hear someone talk about galaxies too old for their redshift, what you're often hearing is a degeneracy problem. The code is allowed to choose an older stellar population because the colors can be fit that way, even if the physical interpretation is uncomfortable. The solution is not to forbid old stars by decree, but to add data that break the degeneracy: spectra, mid-infrared points, longer wavelength photometry, or independent constraints like size and morphology. Sometimes the best solution is simply to widen the space of star formation histories. Early galaxies may not form stars in a smooth exponential curve. They may form in bursts, pause, reignite, merge, and burst again. If your template library assumes a smoother history, it can misinterpret the light. And there is one more quiet factor: the initial mass function, or IMF, the distribution of stellar masses at birth. Most SED fitting assumes an IMF similar to what we infer locally, because we don't have strong evidence for a radically different IMF at high redshift. But even modest differences in the IMF can change the mass-to-light ratio. This is not a claim that the IMF is different. It is a reminder that mass estimates always live inside assumptions. When Webb forces us to confront these layers, the result is not confusion. It is clarity about what we are actually assuming. If you like, think of it this way: early Webb results didn't just show us distant galaxies. They showed us the skeleton of our inference machinery. They revealed which joints were stiff and where we needed more flexibility. In the next file, we'll use the idea of compactness as an additional constraint, and we'll connect it to reionization and black hole growth in a calm, sleep-friendly way. Compactness is a quiet clue. When Webb sees a little red dot, part of the reason it stands out is that it looks small, sometimes almost like a star in the image. But it is not a nearby star, it is a distant object, and if it is distant, then appearing small means the source is physically compact. In galaxy evolution, size matters. The size of a galaxy is shaped by angular momentum, mergers, feedback, and the distribution of gas. In the early universe, densities are higher, merger rates can be higher, and gas inflows can be more dramatic. So compact galaxies are not surprising in principle, but an abundant population of extremely compact red sources with unusual spectra is a specific thing, and that specificity is what draws attention.
If LRDs are host accreting black holes, compactness makes sense. The region near an accreting black hole is small. The broad line region is small. The central engine can dominate the light from the core of the galaxy, making the overall appearance point-like. If LRDs are compact starbursts, compactness also makes sense. Star formation can occur in dense central regions, especially if gas funnels inward. A compact burst can be dusty and red, and if the burst is intense, emission lines can be strong, influencing observed colors. This is why LRDs are fascinating. Multiple plausible scenarios produce the same high-level appearance. So how do we break the degeneracy? One route is spectroscopy. Broad permitted emission lines can indicate fast-moving gas, often linked to accretion. Line ratios can indicate ionization sources. But even these diagnostics can be complicated by dense star formation. Another route is mid-infrared information. Dust warmed by an AGN can have a different signature than dust warmed by stars. If mid-infrared colors are modest, that can complicate a strong AGN interpretation. But these diagnostics are challenging at high redshift, and the objects are faint. A third route is clustering. If LRDs are mostly AGN, their spatial distribution might reflect the distribution of black holes and massive halos. If they are mostly star-forming galaxies, their clustering might look more like the general galaxy population. Clustering analyses are subtle, but they add an independent constraint, one that doesn't rely only on light fitting. And then there is time. If we monitor a source and it varies significantly, that can be a clue. AGN can vary on certain timescales. Compact starbursts can also have variability in some regimes, but the pattern differs. Time domain astronomy in the early universe is difficult, but it is a growing frontier. Now let's connect compactness to a broader cosmic question: reionization. In the first billion years, the universe underwent a transition called reionization. After the cosmic microwave background era, the universe was filled with neutral hydrogen. As the first stars and galaxies formed, their ultraviolet light began to ionize that hydrogen, making the intergalactic medium more transparent. The details of which sources drove reionization, massive stars, faint galaxies, early AGN, remain an active area of research. If LRDs represent a widespread population of faint AGN-like sources at high redshift, then they could contribute to the ionizing photon budget in ways that are still being quantified. If they are compact starbursts, they could contribute as well, especially if their geometry allows some radiation to escape. This is part of why the LRD puzzle has significance beyond classification. It touches a key phase transition in the universe's history. It also touches black hole growth. If the early universe had many compact AGN-like sources at high redshift, then black holes may have grown rapidly and widely. That would feed into the question of how supermassive black holes became so massive so early. The tone in popular coverage can be dramatic, but it points at a real scientific tension: growth rates and timelines. Again, the calm approach is to treat this as a constraint problem. Webb is giving us more constraints. Models will accommodate them by adjusting seed masses, accretion duty cycles, obscuration fractions, and feedback efficiencies. The story will not settle overnight. It will settle slowly as the dataset grows. If you want a gentle question here, do you find it more compelling to think about the first light of galaxies or the first hunger of black holes? Comment first light or first hunger. Next, we'll pull back to the bigger anomaly theme. When data and models disagree, how do scientists decide whether the disagreement is a measurement issue, an astrophysics issue, or a deeper cosmology issue? We'll talk about what thinking again looks like in practice. There is also a practical measurement question hiding here. How do we measure small at the edge of resolution? Every telescope has a point source function, the blur pattern of a point source. For Webb, that blur is impressively tight in the infrared, but it is not zero. So when a source looks point-like, astronomers often use careful modeling to deconvolve the image and estimate whether it is truly unresolved or merely very compact. This is another place where early interpretations can shift. As processing improves and as multiple exposures and instruments are combined, size estimates can tighten. Some sources that were first described as nearly point-like can later show slight extension. Others remain stubbornly compact. If a source stays compact even under improved analysis, that becomes more informative. A truly compact galaxy in the early universe may represent a high-density stellar system, perhaps a precursor to a bulge or a compact quiescent core. If it is an AGN-dominated source, compactness is expected. But then the next question becomes, what is the host galaxy doing in the background? Is it forming stars? Is it obscured by dust? Is it small because it is young, or small because it is being sculpted by feedback? A calm way to gather more constraints is to compare different mass measures. Photometric stellar mass estimates come from light, but dynamical mass estimates can come in some cases from gas motions, line widths that reflect gravitational potential. These measurements are hard at high redshift, but they are part of the longer-term plan for making the story less ambiguous. Now, let's connect compactness to reionization, because it connects compactness to cosmic impact. In reionization, what matters is not only how many photons a source produces, but how many escape. A compact, dusty galaxy might produce many photons, but trap them. A porous geometry might let more escape. An AGN might produce hard radiation that travels differently through gas. So if LRDs are abundant, and if their radiation escapes efficiently, they could matter even if each individual source is not the brightest thing in the sky. This is why astronomers treat populations as important. Even modest sources, if numerous, can shape the universe. And if you hold this thought gently, it becomes almost soothing. The universe changes not only through violent events, but through the sum of many small, steady influences. In the next file, we'll look at how scientists decide which layer of the modeling stack to adjust. We'll do it calmly, as a kind of method, something you can recognize across many areas of science.
When data and models disagree, there is a quiet sequence most scientists follow, even if the headlines don't mention it. First, check the pipeline. Calibration, background subtraction, selection effects, lensing contamination, photometric redshift degeneracies, completeness. These are not the glamorous parts, but they are where false anomalies often live. Second, check the astrophysics assumptions. Stellar population models, dust laws, emission lines, star formation histories, IMF assumptions, feedback prescriptions. These are the middle layers where reality can be more diverse than the library. Third, check the cosmological context. Number densities, halo mass functions, growth rates, and the mapping between observable properties and underlying structure. Most of the time, the resolution emerges in the first two layers, but sometimes the tension remains and moves upward.
This is why the Webb anomalies conversation has been productive. It has forced the community to improve tools and to test assumptions. In doing so, it has also clarified what is actually anomalous and what is an artifact of early interpretation. One recurring theme is that rare objects may be more visible than expected because surveys are small and cosmic variance matters. If you look at a small patch of sky, you can, by chance, land on an overdense region with more bright galaxies. As surveys expand, averages become more stable. Another theme is that rare phases may have high duty cycles at early times. If galaxies go through bursts, brief periods of intense star formation or accretion, then you might catch more of them in a bursty phase than simplistic models predicted. Another theme is that dust and obscuration might be more significant earlier than assumed. Dust can hide star formation in visible wavelengths, but make galaxies bright in infrared. Dust can also make objects look older or heavier if you don't model it correctly. And then there is the mechanism we have circled around all episode: mixed light sources. In the early universe, a compact accreting black hole and a compact starburst can coexist. If your fitting method assigns most light to stars, you overestimate mass. If it assigns most to an AGN, you underestimate star formation. The truth is sometimes in the blend. This is why the LRD debate is so valuable. It forces the community to sharpen diagnostics, to use multi-instrument data, and to think carefully about the difference between galaxy light and engine light. If you listen to this like a bedtime story, let the moral be gentle. Uncertainty is not a flaw. It is the space where discovery lives. Now to the phrase in your episode title, things that make the model think again. Here's a calm way to phrase it. Webb is forcing models to become more realistic about early environments. It is forcing simulations to include more accurate treatments of dust, radiation, and feedback. And it is forcing observers to refine the light-to-mass conversion with better spectral templates. And it is forcing theorists to consider that early black hole growth might be less rare, more obscured, or more efficient than some earlier assumptions. That is not a crisis. That is a sharpening. If you want a small interaction prompt, do you prefer episodes that emphasize the detective work, how we validate and revalidate data, or episodes that emphasize the big implications, what it means for our picture of the universe? Comment detective or implications. Next, we'll return to the early universe timeline and connect these anomalies to a broader narrative. How quickly structure emerges, why maturity can be misleading, and how cosmic time can compress dramatic growth into what feels like an impossibly short window. A helpful idea here is cross-validation. When a surprising result appears in one dataset, the first question is, does it appear in another independent dataset? Different web programs observe different fields. Some use different filter sets. Some use different reduction pipelines. If an anomaly repeats across independent surveys, it becomes harder to dismiss as a processing artifact. The next question is, does it appear with spectroscopy? Photometric selections can be efficient, but spectroscopy is anchoring. When spectra confirm a redshift and reveal line properties, the interpretation space narrows. This is why in the Webb era, the community has leaned heavily into NIR spec follow-up programs. Then comes comparison across wavelengths. If a source is dusty, far infrared and sub-millimeter observatories like ALMA can help measure dust and gas. If a source is an AGN, X-ray observatories and radio facilities can help, though obscuration complicates this at high redshift. Each wavelength adds a different kind of evidence, like different senses in a quiet investigation. And then comes the statistics.
Scientists ask, how likely is it that we would see this many bright objects by chance, given the survey area and depth? What is the expected cosmic variance? How sensitive are the conclusions to the choice of priors? How do results change if we require consistency with multiple diagnostics? Sometimes the outcome is that the anomaly is real but smaller than first thought. Sometimes the anomaly is a selection effect. Sometimes the anomaly points to an astrophysical regime that was under-modeled. And occasionally, after all that, the anomaly remains as a genuine tension that invites new physical ideas. This is why the anomaly word can be comforting if you let it be. It does not mean broken, it means not yet explained. If you enjoy calm, you might enjoy this meta-thought. The early universe is teaching us how to think. It forces us to separate what we observe from what we infer. It forces us to ask which assumptions are doing the heavy lifting. It forces us to become more careful, and that care is a kind of quiet discipline. Next, we'll return to the compressed timeline again, because the timeline is where the emotional feeling of too fast comes from. We'll make that timeline feel less impossible and more like what it really is, a different scale of time where exponential processes can change everything quickly. One reason early universe anomalies feel so intense is that cosmic time is compressed. When we say the universe was 600 million years old, it sounds like a long time in human terms. But in cosmic structure formation, 600 million years is a short window. It is a period when density contrasts were still growing, when gas was still settling into halos, and when the first heavy elements were still being forged. So, when Webb finds a compact dusty galaxy, or a luminous active nucleus, or an object with a surprisingly evolved-looking spectral shape, it triggers the same question. How did it happen so fast? There are a few quiet answers. One is that growth is not linear. It can be exponential under the right conditions. A black hole that accretes near its maximal sustainable rate can grow rapidly over certain timescales. A galaxy in a dense region can experience frequent mergers and continuous gas inflow, accelerating assembly. Another answer is that mature looking is not the same as old. A dusty galaxy can look red and evolved even if it is young, simply because dust absorbs the blue light. A spectrum can show strong breaks or red slopes that mimic age. Another answer is that early environments are extreme. Gas densities can be high. Cooling can be efficient in some regimes. Feedback can be intense, but it can also be directional, allowing inflow and outflow to coexist.
The early universe is not a quiet, uniform stage. It is a turbulent one. And another answer is that our selection is biased towards the bright and the unusual. Webb reveals the bright tail of the distribution early. As surveys deepen, the faint majority becomes clearer and the context changes. This is why it's helpful to think of Webb's early anomaly era as a rebalancing of our expectations. Before Webb, the early universe was partly inferred. After Webb, it becomes directly populated with objects. The distribution is no longer hypothetical. It has texture. The little red dots add a specific texture. If they are abundant at certain redshifts and then fade from view by later epochs, it implies a phase, something that turns on and then turns off. The phase could be a period of obscured black hole growth, or a compact starburst mode, or a transitional stage in galaxy assembly. The fact that they appear concentrated in a particular era is itself a clue, and it raises one of the most interesting quiet questions: what do little red dots become? Some popular reporting has suggested that at least some little red dots could be early stages of galaxy and black hole growth that later evolve into more familiar active galaxies, perhaps after shedding dust or after their central engines change state. That's plausible in outline, but the details remain open. Evolution is not one-to-one. Populations can branch. Some little red dots may merge into bigger systems. Some may quench. Some may simply fall below detectability. If you think of it like ecology, it can help. The early universe might have many juvenile species, short-lived forms that are common in early environments but rare later. As conditions change, those forms either evolve or disappear. JWST's continuing surveys and spectroscopy programs are in effect building a census of the early ecosystem. Each year adds more members to the catalog, more spectral classifications, more constraints on size, mass, dust, and line properties, and each year the parameter narrows. If you want a calm interaction prompt, when you hear early universe, do you imagine it as a quiet, empty place that slowly fills up, or as a crowded, chaotic place that quickly organizes? Comment slow fill or chaotic start. Next, we'll take one more pass at the too many bright galaxies issue, but in a way that respects what we now know. What observations actually remain in tension, what has softened, and what kinds of future data, especially spectra and larger area surveys, will decide the story. If too fast is the feeling, it helps to remember that the early universe is also too dense.
If you want a final interaction prompt before we close, do you prefer mysteries that resolve into "we measured better," or mysteries that resolve into "the universe is stranger"? Comment "measured better" or "stranger." In the final file, we'll close gently. We'll summarize what these anomalies teach us. We'll keep the tone calm, and we'll end with the feeling that the early universe is not a scandal. It's a frontier, quiet, distant, and patient. In practical terms, the next steps look like this: larger samples, wider fields. Deep fields are powerful, but they can be unrepresentative. Wider area surveys reduce cosmic variance and help measure true number densities. Better spectroscopy. Spectra confirm distances, reveal line widths, and help separate star formation from accretion. More mid-infrared constraints. Dust physics and obscuration are central, and longer wavelengths help. multi-observatory synergy, ALMA for dust and gas, Hubble for complementary wavelengths where useful, X-ray observatories for high-energy signatures, and upcoming facilities for even deeper characterization. And consistent modeling frameworks, community pipelines that allow apples-to-apples comparisons across surveys. And on the theory side, simulations with improved dust and radiation transfer, models that capture bursty star formation and episodic accretion, more explicit treatment of obscured phases, so the visible universe is not assumed to be the typical universe, and better statistical comparisons that reproduce survey selection effects. If you're listening as you fall asleep, the details aren't the point. The point is that science has a plan. It doesn't depend on a single dramatic result. It depends on repeated measurement and consistent interpretation. And that makes the anomalies feel less like threats and more like invitations. If you want one more soft question, do you want future episodes to spend more time on the instruments, how telescopes actually see, or more time on the theories, how models turn matter into galaxies? Comment instruments or theories. Now we can close. Let's end the way we began, slowly. In this episode, we stood at cosmic dawn and watched the data do what good data does. It surprised us. Then it asked us to be careful. And then it offered a deeper kind of clarity, one that comes from not a single headline, but from the steady narrowing of uncertainty. We talked about the early reports of galaxies that looked too big too early, and we held that story with gentle skepticism. We reminded ourselves that early mass estimates were often based on photometry and on templates that may not have captured all the ingredients of early universe light. We noted that later work revised some estimates downward and softened some tensions. We talked about the stack of modeling layers, calibration, astrophysics, and cosmology. And we treated the model must rethink as a process of refinement rather than a dramatic collapse. And we lingered on the little red dots because they are the most poetic kind of anomaly, simple to describe, difficult to classify. We held multiple hypotheses: dusty, compact starbursts, faint, obscured AGN, mixed systems, and more speculative ideas, and we treated each as a hypothesis, not a certainty. Now here is the quiet takeaway. The early universe is not a tidy place. It is dense, energetic, and fast. Growth can be bursty, light can be blended, dust can hide and reveal at the same time. A compact object can look like a point and still contain a galaxy's worth of physics, and a model, no matter how successful, must remain willing to expand its library of possible behaviors. If you want one last gentle question, let it be this: what do you enjoy most about these frontiers? The fact that we can even see this far back in time, or the fact that the universe still has the power to surprise us? If you want to comment, write seeing or surprise. And now we can let the episode fade. If you're enjoying the quiet universe, you can support the channel in a very quiet way. Like the video, subscribe, and share it with someone who enjoys calm, science-based stories for sleep. That small support helps me keep making long, gentle episodes.
more cosmic dawn, more deep fields, more quiet mysteries, without turning them into noise. Thank you for listening. Let your breathing slow. Let your thoughts soften. And let the early universe drift away behind you, still strange, still beautiful, and still patiently waiting for our next question. Before you drift off, let me offer one last way to hold this story. Imagine the early universe as a shoreline at dawn. The light is low, the shapes are incomplete. A few silhouettes look larger than they should. A few points of light are unusually red. You can't yet tell whether you're seeing distant ships or reflections or a trick of mist. So you wait, you watch, you change your angle, you bring a better lens. That is what Webb is doing for us. It is giving us a better lens, but it is also reminding us that interpretation takes time. In the coming years, the little red dots will likely become less mysterious. Some will be classified as compact AGN. Some will be classified as dusty starbursts. Some may remain strange for longer, and that's okay. The early universe doesn't owe us simplicity. And the oversized ancient galaxies story will also become clearer. The most extreme early claims will keep being tested and retested. Some will hold up in a more moderate form. Some will fade as templates and methods improve. The outcome will not be a single sentence. It will be a distribution, an updated map of what cosmic dawn really contained. If you're still awake, you can help in a surprisingly real way. Even a quiet channel like this benefits from signals that tell the platform the content is valuable. A like, a subscription, a share. You don't need to do it loudly. You can do it like a whisper, and then let the universe go back to its slow work. For now, let the questions stay open, but not heavy. The early universe is far away. Its surprises are gentle. And the next answers will arrive the same way the light arrived, slowly, patiently, across a very long distance. And if you want to leave a final note for this episode, keep it simple and soft. What part stayed with you most? The oversized galaxies, the little red dots, or the idea that models can evolve without breaking? Write just one phrase in the comments. I'll read it, and it will help shape the next quiet journey. Now, truly, we can let the story end. Good night.